Okay, done from my side. Your mic is mute, Varun.
Yeah.
Good afternoon, Sarah.
I think it's good evening there.
Yeah. Sarah, your mic is muted also.
There we go.
Good evening.
Hello, good morning, good evening,
It's
everyone.
dark where I am. A little better. Not much. It's just dark here. Oh, you're joint with JSPS Japan. I didn't know that.
Everybody, hi Sarah.
Hi, Raju. How are you?
I'm doing fine. How are things there?
Okay, I guess we're all just trying to survive and get something done.
Looking forward to your talk.
It's nice to see familiar faces again.
Yeah, I don't know. Varun Chaudhary is one of my group members. Actually, he's one of the organizers.
Oh, okay.
Yeah.
I knew I'd seen the name. I wasn't.
Right. Yeah. And yeah. Hi, Prem.
Hi, good morning.
Morning.
So are you all back at NTU?
We're all here. There are some travel constraints on the government side to go in and out, and also NTU is kind of discouraging people from traveling.
From traveling, but you can go to the university.
You can go to the university. There are some restrictions. There are some restrictions on face-to-face meetings.
Mm.
Next semester, that may be lifted. But this semester was almost everything was online. All our teaching.
Oh, really?
Yeah.
Wow.
Only a few tutorials. The small groups were face-to-face.
Well, this
Yeah.
semester we were able to do face-to-face with everything, but with the Omicron, 900 students at Cornell got sick.
Oh, I never read that. Wow. That's
And so they
huge
switched yeah, that's a huge number.
Wow.
And so they're having final exams online.
Wow.
Princeton's putting final exams online. NYU, all these
I
places.
see. 900 is
900. How did that happen? That's
Yeah.
with, when we have 98, 99% of the students and faculty and staff are vaccinated. So that's
Oh my.
horrifying.
Yeah, I hope that it's effective against this latest variant, right?
Me too.
Yeah. Yeah, I think most of us here in Singapore who are eligible, either by choice or by government rules, have are vaccinated. It's a very high percentage, more than 90%.
Very high percentage cure, certainly of university people.
Right. So, but there are still cases. Sometimes they do this deep cleaning of labs because of the somebody has been diagnosed with COVID. So that's how we come to know that somebody in the university is. They used to announce, but then they stopped.
Yeah, well, we get the announcements, but only when the clean room has somebody who's been exposed.
Okay.
It's kind of funny that like the one place where
it's clean, so-called clean.
Probably okay.
That's interesting. Yeah.
Okay, let's get started.
Yeah.
Good morning, everyone. Welcome to the 11th Annual Symposium on Magnetics. IEEE Magnetic Society Singapore chapter has been organizing this annual event for the last 11 years. So we have been having speakers from overseas as well as we have local speakers. And the highlight of this particular symposium is that we always hold a competition for the student presenters. So this gives them confidence to present in conferences, and the competition element always excites the student. So this year also we have the 11th annual symposium. This year Varun has taken the lead in organizing the symposium. So he is one of the co-chairs. So he will also chair the first session. So I welcome you all and pass the mic to Varun. Varun, please go ahead.
Yeah, thank you, Prof. So welcome everyone. I'm Varun Chodri, Senior Research Fellow in School of Material Science and Engineering, NTU Singapore. Thank you very much for joining this IEEE Magnetic Symposium 2021. So this is a two-day symposium, and we have plenary, keynote, and invited talks, and also student competitions. We also have a special talk on entrepreneurship tomorrow morning. Some instructions before starting. So other than speaker, please mute your mic all the time. And we will be having some time at the end of every talk for questions. So you raise your hand and you will be asked to unmute yourself and ask the questions. So current session start with the plenary talk by Professor Sarah Magitek. She will be talking on very interesting topic, super paramagnetic tunnel junctions for probabilistic computing. Sarah Magitek is a professor in physics at Carnegie Mellon University. She received her AB degree in chemistry at Princeton University, master degree in physical chemistry from Columbia University, and PhD in physics from University of Georgia. Her research interests are in magnetic nanostructures and their applications. She developed methods to synthesize monodisperse magnetic nanoparticles and self-assemble them into ordered 2-dimension and 3-dimension arrays. Her current projects include superparamagnetic tunnel junctions, magnetostatic logic, and magnetoresistive detection for fermions. She has a very big list of distinctions and awards for her contribution to science and teachings. Some of them are National Young Investigator Award from US National Science Foundation, Distinguished Lecturer of IEEE Magnetic Society, Fellow of American Physical Society, and Fellow of IEEE, and so many others. Thank you, Sarah, for accepting our invitation and make yourself available even at this is a night time in Pittsburgh. So welcome, Sarah, and please start sharing, and looking forward to your interesting talk.
So thank you very much. It's a pleasure to be here. I wish I was there in person. I wish we were all able to meet in person, but until then, again, I really am glad to have a chance to tell you more about what we're doing and to see the familiar faces of many of you in Singapore. So what I want to talk about tonight, well, this morning for you, is a little bit about our work on superparamagnetic tunnel junctions. And so with our tunnel junctions, everything I'll talk about has two magnetic layers and a tunnel barrier, MgO. Our layers are, in all cases, cobalt iron boron. And the difference between this and a standard tunnel junction that you may be more familiar with is that one of the layers is superparamagnetic, meaning that it is switching spontaneously between either perpendicular up and down or to the right and to the left magnetization, depending on whether we have a perpendicular tunnel junction or an in-plane tunnel junction. But in either case, the resistance across this tunnel junction is going to vary in time, and there'll be two levels, two characteristic levels, and the time that it spends before switching back to the other level is going to vary stochastically. So what I want to discuss is a little bit, as I introduce, what are superparamagnetic tunnel junctions, but to say what they might be good for. And people know superparamagnets as particles are good for and interesting for a lot of things. But there's different applications involved with the superparamagnetic tunnel junctions. I want to discuss two of them first and explain the strategies for designing a superparamagnetic tunnel junction for a particular application with electrical control, of course, and then say a little bit about what I think is the most intriguing application, which is probabilistic computing. So I want to explain how that works and why you should care about integer factorization, but then get back to the physics of the dynamic Ising model and show some results that we've got for a NOT gate and an AND gate before finishing with a little bit about future work. So, okay, next. Is it not? It's not switching. Oh, okay. So again, a superparamagnetic tunnel junction is a regular tunnel junction with a superparamagnetic free layer. And so if we're looking at current as a function of time, then the parallel state would have high current, the anti-parallel would have low current. And if you have a big barrier, you would have a fairly long dwell time on average before the next switching event. If you have a low barrier, then you'd have a short dwell time before switching events. And the relative, in the case of current, the parallel is high, current, anti-parallel is low. If we're looking at resistance, it would be the opposite. In either case, there's a lot of work that's been done to develop tunnel junctions for memory, for MRAM. And usually there, you're thinking about a parameter for the thermal stability, this delta, which is the energy barrier height relative to the thermal energy, that should be on the order of 60 to 80. People who work with magnetic recording media are also using this parameter. But for probabilistic computing, you want a really low barrier because you want the switching to happen quickly. So if you're relying on a time average, you want a lot of events within a short time period that you can average and get a statistical average of the property. So let's see, get next. Okay. So some of the earliest work that we did with this, we used a field to... Is there a question? Is there a question?
No, please go ahead. Someone mic was on. Yeah.
Okay. So some of our earliest work, we were able to do this, control the superparamagnetism with an external magnetic field. And here we had a perpendicular tunnel junction with the free layer on top. So it could be magnetized up or down, switching back and forth. And if you did a hysteresis loop, you would get the black curve. You ramp the field and you see a switching from, in this case, low resistance to high resistance. Sorry, my dog is...
I'm sorry. I think someone...
No, that's my dog.
Mute yourself.
I can't mute myself because that's my dog.
Oh,
sorry.
Okay.
Sorry. He will settle down. Sorry.
Oh, I thought it's someone else. Okay.
No, he's fine. So you would see this black curve, and this is with a particular ramp rate of the magnetic field. If you were to sit at a fixed field, shown in all the colored dashed lines, and measure the resistance as a function of time, you'd find that in the hysteretic region, it's actually switching once in a while back and forth, 130 Ersteds. It's spending most of its time in the anti-parallel state for high resistance. But if you go down to 113 Ersted, it's spending most of its time in the parallel state for low resistance. And so over a very small applied magnetic field, we can tune the behavior. We can change what the time average is. And what this gives us is what we call the sigmoid curve. This is this red curve. If we were to look at the time averaged outputs for all the different applied fields. And the sigmoid curve is going to be important for a lot of the applications that I discuss later in the talk. But what is different is we want to be able to get a sigmoid curve, not with an applied magnetic field, but with a current or a voltage or a stress or some other kind of controllable parameter. And that has to do with the miniaturization. If you want to have a circuit, a chip that has many of these devices on them, 100, 1,000, whatever, you're not going to be able to have an independently controlled magnetic field for each of them. You're going to have to do this electrically. So fortunately, with magnetism, we've got lots of options. We've got voltage-controlled magnetic anisotropy, spin transfer torque, and spin orbit torque that we have worked at. And so I'll tell you a little bit about those, though we won't do a lot with spin orbit torque. We have done it for switching for MRAM kind of devices. So it certainly is feasible. It's just more wiring involved. So it's a little bit more complicated. But what we were able to see is this effect can be used to switch or to look and characterize devices as small as 20 nanometers. So you really can get down to small sizes. The question is, what kind of design and what kind of electrical control is going to be best for particular applications? So of the potential applications, random number generators are a big one. Again, right now, this is done with software mostly, but the software random number generators aren't really random. And so they need hardware RNGs to help with encryption. And everybody knows that their passwords are having to get longer and longer. And people are trying to steal our information. So, random number generators are an important application. Analog multiplication is another one. And, both of these are examples of things that our existing CMOS technology does not do particularly well. There's not going to be an easy drop-in replacement for CMOS for a lot of applications. It's very good. And a lot of money and many people's work have gone into developing it over the years. And so one of the strategies that we have is to look at places, like graphics processing, different things where it's not ideal, where there's options for niche applications where magnetic devices could in fact be better. And so in the probabilistic computing area, random number generators, analog multiplication. One really interesting one is invertible logic gates. So if you know the output, what are the probabilities for the different inputs that lead to this? So this could be very useful for decryption. Integer factorization is also a big application. I'll say more about that later. And then there's lots of optimization problems that are typically solved by computers, by software, but really could be done with hardware with these superparamagnetic tunnel junctions. And finally, a whole area where these tunnel junctions might find applications would be for low energy computing. And so that's not for your supercomputer where you want performance and you want it fast and you want many, many, flops in your calculation. But if you need low energy where, you might have a lot of Internet of Things remote sensors, or where you don't care so much about time, but you do care about energy. So you want your cell phone battery to last longer. You don't need streaming video to be working on a 10 nanosecond timescale. The timescale, the natural timescale is the timescale it takes for you to swipe your finger across your phone. So there are lots of possible applications. Right now, we're looking at really the devices themselves and the physics of the devices and trying to get them to work. And so we'll talk about two specific cases. First, the random number generator, where we use a perpendicular MTJ and voltage controlled magnetic anisotropy. And so because it's voltage controlled, you're not sending much current across this, you're not going to damage the tunnel barrier. You can get, with low power, you can get tunability. And here's some data showing what happens as you change the voltage a few tenths of a volt between the average dwell times. I apologize for these little blips. That's noise from our other electronics. But the sort of got long times for the switch for the dwell times between switches, and sorry, neutron is speaking up. But what you see is that with a few tenths of a volt change, you can make the average dwell time shorter. And you can make it look like grass, if you go to -1 volt. So you can have a big, you can have a big difference with a small difference in the applied voltage. However, you do not get the sigmoid curve that you need for some of the other applications. And that you can see when in the top trace, you're going, it's not 50-50, but it's not far from it. In the bottom trace, it's roughly 50-50. So you're not going from 0% to 100%. So anyway, excuse me. Sorry. So if you get to the analog multiplication, which is a different example, here you're looking at taking two probabilistic inputs and putting them into a CMOS AND gate. And you can show that if you look at the time average of one input, let's say both inputs are the same and they have a time average of X, you take the time average of the output, you get just X squared. So it's really the time average of the output is the product of the time averages of the two inputs. And so for this, instead of using a perpendicular tunnel junction, we use an in-plane magnetization. And the difference with in-plane magnetization is you can really tune that average lifetime in the parallel state or the anti-parallel state, not just 10%, you can go orders of magnitude. And by changing it by orders of magnitude, you are able to get this full sigmoid behavior. And if we look at the application of analog multiplication, what we find is that if you look at the time average measured over very long time, you get a very good approximate to this product. If you're measuring over a smaller number of cycles, there is some error, but that's saying that you really want devices that are switching with low energy barriers. So you're seeing that the average time is very small between switching events. So these devices, if we're looking at a resistance versus bias voltage, what you would observe is something that shows what I'm showing in red is the sigmoid curve. Excuse me. Sorry about that. Somebody has not gotten enough attention today. So anyway, back to the resistance versus bias voltage. What you find is that here, because these devices are switching so fast, we don't see an open hysteresis loop as we ramp the bias up and then back. what you see is this sort of grass as it's switching back and forth between the two states, the parallel and the anti-parallel. And if you are to go and look at this as a function of voltage and sit at particular bias voltages, then you see that, again, it is spending at 0.17 volts, is spending most of its time in the low resistance state, occasionally going to high resistance. If you go to 0.38 voltage, it's mostly in the high resistance state and occasionally dropping down. But again, in this particular device, 20 by 60 nanometers, we were getting sort of millisecond time response. And so we wanted to get faster than that. And we went to circular dots. And here, we still have a pinning layer, so it's still uniaxial. We still have two levels, but here we can reduce, we can, see this get even faster electronics. And if we apply a small local field of about 7 Ørsted, we can shift this to cancel the local field, and we can shift this to be around 0. So you really could have low power if you have in-plane magnetization for the devices. And with the low power, we've also been able to get this much faster. We've been able to go down to milliseconds, or not milliseconds, microseconds and below. And we can get an idea of what our time resolution is by looking at the number of counts. If we're looking at number of dwell times that are, 500 nanoseconds, 1 microsecond, et cetera, we see that for most of this decay, we're getting Arrhenius law behavior. So we see this exponential decay. If we go down to about 200 nanoseconds or below, we're seeing deviations because of how we're binning, but that really has to do with the electronics that we're using. What we think is that this Arrhenius law behavior works down to sort of tens of nanoseconds. When you get into that regime, then an Arrhenius law for the energy barrier really isn't appropriate. And you would have to do the modeling with Landau, Lifshitz, Gilbert theory. But even in the sort of nanosecond kind of timescale dynamics, the probabilistic approach would work. It's just that the Arrhenius law wouldn't be appropriate anymore. What we see is here's our experimental sigmoid curve. And here is the theoretical prediction or computational prediction by Kiram Chaudhary's group. And so we're seeing this behavior experimentally that they had predicted over about the same range. Again, I mentioned spin orbit torque as a possibility. The last results I was showing were based on spin transfer torque. But the reason that we don't use spin orbit torque is that we need a 3-terminal device in that case. And that just makes the wiring a little bit more complicated. Here's an SEM image of different devices, different pillar devices, dots of different sizes, ellipses, different angles of the ellipses. So we can make these of different kinds of MTJ geometries. But of course, if you want to put them together, you need to hardwire them. And so that makes the nanofab a lot more complicated. But we can do that, and we can make little chips in chip carriers that have lots of individual devices and wire bond them, and so we can connect them to each other. If you look at the individual devices in SEM, there are these flower patterns, and and in the flower pattern, the little X's on one level are the top connections. So we have 4 places we could wire bond, and the other red connections are the bottom electrode connectors. So if we look at a side view of our MTJ, we still have the MTJ on the inside, but now instead of being a bare pillar, we have it surrounded by silicon nitride. So that prevents edge oxidation. We can go in through the bottom electrode. Here we've got platinum coming down. connecting to the tantalum ruthenium layer underneath the tunnel junction. And then at the top electrode, we've got platinum coming down here. And so underneath each of one of these flowers is a single MTJ. So we take these and for the probabilistic computing applications, we need to have several of them coupled together. So first I want to explain why you would want several coupled together and really what they're doing in hardware, which many of you are familiar with in software already with Monte Carlo simulations, and then show some of the results. So there was a beautiful paper by Kiram Chamsari and Hideo Ono a few years back looking at integer factorization. So of course, integer factorization, if you take a small number, you can look at the prime multiples, or you can look at, powers of 2. But as you solve it with a computer, if you've got a low number, computer just starts and divides by all the sequential digits to see where what numbers it could possibly be factors. And that's fine if you've got small numbers, but as numbers get bigger, it becomes a lot trickier. And here's an interesting thing that you may or may not know about, but you certainly should if you're in this area. It's called the RSA Challenge Numbers, and RSA stands for Rives, Shamir, Edelman, and they've developed a way to encrypt data using private decryption keys that depend on knowing what prime numbers are factors of a huge number. So RSA 240 is this number. So 240 digits. And since all of you are really good at math, I'm sure you quickly recognize what numbers, the prime numbers multiplied together lead to RSA 240. So again, think about wanting to do this on bigger numbers than that. The issue is how fast they could be and how much they'd cost. So you can get a pretty good processor from Intel for a few $1,000s, but if you use that, it would take you 900 years. And so there's a real need to do this better. And right now, there's a challenge number, RSA number, that has 2,048 digits. And if you can do this, you can earn $200,000. So this is not the motivation for us going into probabilistic computing, but it shows that this is really important to be able to do. And if there are hardware approaches that would make it faster, there may be niche applications. So again, if we look at how our computers are going to treat this, they're going to break up our numbers into powers of 2. And there's coefficients for the different powers of 2. And so if we have our 2 primes, they would have, in this case, 3 coefficients each. And so a simple question would be, how could we figure out what these factors are with an experimental system? So want to differentiate probabilistic computing from quantum computing. Quantum computing is very elegant, very exciting. I think a lot is being done on it right now, but there are some real challenges. Entanglement over large areas, long coherence times, the fact that you need low temperature, the fact that you need to be able to create a superposition state, let it evolve coherently, and then read it out, switching from isolation that is needed for the superposition state to connection to the outside world. So still a lot of challenges. Nobody's going to have a really big quantum computer tomorrow. I know that Berkeley has a group that has 8 qubits on one wafer. But it's still quite a challenge with the p-bits. you don't need really low temperature. It can work at room temperature. The technology already exists. This could be available in the near future. So, and there's some things that you might want to do with qubits that you can also do with p-bits in a slightly different way. P-bits will not do everything that qubits do, but p-bits will be around much sooner. So one of the examples that everybody discusses with quantum computing has to do with Schrodinger's cat. And the poor quantum cat is in a superposition of states where it's alive or dead. And those could represent the ones and zeros. And the coefficient A1 could indicate the probability that it's going to be in the alive or the dead state. And we're going to name Boltzmann's cat for probabilistic computing. And it would also have two states, but Boltzmann cat is fluctuating between the two states. And you figure out the coefficient A1 by measuring many, many times and calculating how often is it in state 1 and how often is it in state 2 and finding the time average. So it's non-destructive in that way, at least to our poor cat. And so if we think about how you would build up a computing system based on these probabilistic bits, what you're really doing is you want to be thinking about statistical physics and microstates. And what are the possible microstates? You know that, again, in this case, you know, microstates are one, or our probabilities are ones or zeros, but the microstates that are going to be the lowest energy are going to show up most often and have the highest probability. So if we now think of this in terms of spins, because we want to do this with magnetic systems, we can think of an Ising model, spin up or spin down. And really what we're doing is we're calculating the energy, looking at in our interacting spins at what happens with the sort of exchange-like term and a Zeeman-like term. And so statistical physicists have been doing calculations with nanomagnets or with interacting spins for many years, but it hasn't been translated into something that was an actual device until the combination of nanomagnets with electrical control was began to be investigated. So that's what we've been interested in. And again, in our interacting nanomagnets, it's not required that you have a Heisenberg or an Ising exchange, but there is some sort of weighting function and there is some sort of behavior, some sort of characteristic of magnetic device 1 and magnetic device 2 and interaction between them. And then there's an offset-like term, a Zeeman-like term. And so this offset is not necessarily a magnetic field. It could be a voltage, it could be a number of things. So, but what you're trying to do in any case is to minimize the difference between your target and whatever these weighting functions are for, in the case of digital computing, factors of, or powers of 2. So that's what you want to find. And so again, if you've done Monte Carlo simulations, you've thought about this sort of problem. The difference here is we're looking to do this with hardware by coupling our superparamagnetic tunnel junctions and also by averaging the output as a function of time. And so again, if we think about the difference between a Monte Carlo simulation and our dynamic model, in a Monte Carlo simulation, you would choose one spin and you would calculate this energy function for the interaction of this spin with all of the others and with the external applied field. And then look at what happens, a certain probability of flipping the spin. Does that lower the energy or not? And then go to the next spin, recalculate, and do this again and again until you minimize the energy. But in the computer simulation, you are freezing the other spins while you do the calculation. With the coupled superparamagnetic tunnel junctions, nothing is frozen. Everything is constantly updating everything else. So that's the big difference. And so again, to do a simple example, suppose we have two spins and we want to consider the 4 possible states. If the up state is spin up, spin up, the up state is called 1, and spin down is 0, then probability of having both of them up, one up, the other down, switch one down, the other up, both down, those are going to be equal probabilities with no coupling. But if we have magnetostatic coupling, so dipolar interactions, that would say if they're side by side, that the coupling is going to favor the anti-parallel configuration. So one up and one down, and the probabilities are going to show up. If we look at our time average, it's going to spend most of its time in states with one spin up and one spin down. So that's the way this works. In hardware, the way it works is we have circuit boards that are triggered together and are able to capture very fast response. And they are connected to 2 coupled magnetic tunnel junctions. And we can control the state of the magnetic tunnel junctions using a voltage programming. Right now, I'm showing them having the same voltage, but they could be different voltages. And that's giving an additional bias. But what we see, looking at one going into the other, the output from the first tunnel junction, if that is a high resistance or a low current, then it's going into reduce the overall voltage in the next one. That's going to shift in such a way so that it is favoring. So way to see this is, okay, when we're looking at our sigmoid curve here that we've got, we could break that down into the average time it's spending in the parallel state as a function of voltage, which is dropping as we increase the voltage, and the average time it's spending in the anti-parallel state, which is increasing. So we decrease the likelihood of the parallel state, we're increasing the likelihood of the anti-parallel state. And there is a voltage where we call the half point, where it's 50-50. And so if we shift one way or another in the bias voltage from the 50-50 point, we are, so 50-50, it's spending on average half time in each of these states. We look as a function of time at the resistance. If we go up in bias voltage, then we are shifting to favor the anti-parallel lifetime. So that's getting longer. If we go down, we're shifting to favor the parallel lifetime. So that's what this shift in the voltage bias is doing. And we can see this experimentally with the simple case of the NOT gate. If the 2 devices are uncoupled and we've got different programming voltages, so the device 1 is spending most of its time in the parallel state, low resistance, once in a while goes to high resistance, anti-parallel. Device 2 is spending most of its time in the anti-parallel state, once in a while drops down to parallel, but they're uncoupled. And you look over different time windows and there really aren't any correlations, it's random. But you hook them up together, and now we see that when device 1 is in the low resistance state, device 2 is in high resistance, oops, and vice versa. Oops. And 95, 98% of the time, we've got this anti-correlation that you would expect, just like you would have for the logical NOT operation. So we're able to see this, and NOT gates are pretty simple to make with superparamagnetic tunnel junctions. On the other hand, you could ask yourself, isn't a CMOS NOT gate good already? Why do we need a superparamagnetic NOT gate? And the answer is we really don't. This is really just a step in the direction. And this is where looking at the more complicated gates, AND gates, 3 tunnel junction gates, that's where you start to see some advantages over CMOS. But they're more complicated. So there are simulations that have been done. Simulations are predicting very, very fast behavior is possible, but they are, there's a lot of assumptions that are made in those. Experimentally, we can certainly get down to, I think tens of nanoseconds is realistic. I think it's going to be hard to get down to fractions of a nanosecond with this. But I do think that the invertibility works. We're able to see evidence of that. But in order to understand the invertibility, we have to understand that we're not going to get as close to deterministic behavior as in the probabilistic NOT gate. And this is just true for all the other tunnel junctions. The easiest example to explain is AND gate, where if we look at the truth table from the mathematics perspective, if you have 3 different gates or different devices, A, B, and C, if you know A and B, you know what C is going to be for the AND gate 100% of the time. If you have these 3 superparamagnetic tunnel junctions representing A, B, and C, you really have 8 microstates, and each of them are going to be equally probable. 4 of those microstates are consistent with the AND gate truth table, and 4 of them aren't. So the strategy in how you hook up these devices with each other is in such a way that you're going to favor the 4 microstates that are consistent with the desired truth table at the expense of the others. So really, one way that we have found useful to look at this is to think about what are the energies. So with the different feedback that you give, how do you choose it such that you have different energies for these states, and that you're favoring the 4 states that you want and heavily disfavoring the ones that you don't. So if you look at them pairwise, you can see of the 8 microstates that there are pairs that differ in the output C, and one of them is consistent with the AND gate and one isn't. And so we're able to design circuits that favor those states. But our probabilities do change, and we do see qualitatively consistent behavior of favoring those 4 states over the ones with the wrong value of C. But it's not 100%, it's not 90%. So we're getting statistical differences, but it's not as much. And so that means that you have to average over a longer period of time, more cycles, in order to get good statistics for your process. And so again, we've been able to look at these statistics. Let me say something about the invertibility, because I think that it's subtle, but it's the most intriguing thing that you could do with these probabilistic gates. And again, it's early in the morning for you, late at night for me, so I don't want to go into great detail on this, but I think a simple picture in terms of an energy level diagram is very helpful. You design your circuit so that if you're letting your 3 tunnel junctions they're coupled together, but you're letting them run freely. You've calculated their energy levels. Then you go back and you take one of those tunnel junctions, the output, and you ramp up the bias, pin it to the anti-parallel state, or ramp down the bias, pin it to the parallel state. So go pin it to a 1 or a 0. And that's going to effectively change the energies of those microstates. So if you measure your system free running, then pin the output. You can work backwards, and by looking at the statistics again, looking at the differences pairwise, you can figure out what the likelihoods of different values of A and B for an output C is equal to 0 in this case, or C is equal to 1. So that's the way this process works, and could be used for decryption. We're able to see this. One of the things that we're able to do that the other groups have not yet reported is we're able to do this working off the 50-50 point. So that makes it more versatile in the decryption. But the integer factorization work that's been done, it's been really impressive. And I think that's another direction that's going to be fruitful for probabilistic computing. So with that, I'd like to just summarize by saying that there are a lot of niche applications where superparamagnetic tunnel junctions may have advantages, including random number generators, analog multiplications, because you don't have to digitize and then do A to D and D to A, and then logic gates because of invertibility and because of lower power. So I think that there's still a lot to be done to speed them up and to optimize the feedback efficiency. But definitely you want these low energy barrier devices. And so I think there's also a lot of materials development work. So much has been done to make big energy barriers for MRAM, for deterministic switching devices. We actually find that low energy barrier devices are better, and soft materials would be better. In plane has advantages just because all of those things lower the energy barrier. And one of the things that we're working on now is extending this to reservoir computing for neural network accelerators. So with that, I'd like to thank the students who participated in this, our collaborators, and our funding agency. So thank you very much.
Thank you very much, Sarah. Thank you for a very interesting talk. Now we'll go ahead and take some time for questions. So audience, please raise your hand and I'll unmute yourself to ask the question.
Hi. Yeah, Vinayak here. Yeah, interesting talk. So I lost first, 10-15 minutes, but later I've I could follow. So one question I have is, do you have the reset issue here? Meaning, once you switch from P or AP state,
Yeah.
Ideally speaking, once it has the spike, so it has to come back to its own initial state. So do you have such problems of reset, or do you need external circuitry to do that?
No, that's the thing about these, is they are constantly resetting themselves. You don't control it. It's flipping back and forth. I mean, it depends on what your driving force is. But if you're driving, say, with spin transfer torque, as long as you continue that spin transfer torque to destabilize it, it's going to flip back and forth. That's the probabilistic aspect of it.
Okay, that's the advantage. Okay, got it.
Right.
And the one you showed today, is it the theoretical work, or do you have demonstration from experiment also?
I just showed the experiments. We're experimentalists, so.
I see. So all the data you showed is okay.
Yeah, this is experimental data.
I see.
This is experimental. This is experimental.
And how many, the kind of size you need, the memory size, or is it on the single bit, or?
How many devices or?
Okay, so let me rephrase my question. So you can achieve this kind of thing by having, small array also, or you could do this kind of thing by having, single bit, right? So this particular results you showed today, is it, done on single device, or, you have verified from?
Well, the logic gates were done on 2 or 3 devices that are
see.
coupled together. These are the hardwired devices.
Okay, thank you.
All right.
I have one question. Hello. Thank you very much for a very interesting presentation, first of all. One question, how the voltages can be controlled in 2 MTG to get desired output signal? Because in one of the slides, they showed the 2 MTGs, I mean 2 devices connected, and you mentioned the voltages can be different voltages applied based on what the signal we want to get. So how can we?
We've got little. Let's say. Let me go to the end. I think I have the circuit. We have little modules of the circuits, and so there are differentiators and comparators.
Yeah, this one. That is previous. Yeah, this one.
Yeah. So, but I mean, this is just very schematic. So do I have it at the end? There we go. Is that what you're asking about?
Yeah, how to control those the voltages, applied voltages to get desired output signal. This is.
Well, first you have to characterize your MTJ. To know, the particular device and what its sigmoid curve looks like. But then we have differential amplifiers, and we've got voltage inputs that we program. And then we use a Wheatstone bridge kind of circuit. So that when we balance it, we can get a sensitive measurement.
I see. Thank you.
Okay, Propraji, you can unmute yourself and ask the question.
Thank you. Sarah, it was a wonderful and very interesting presentation. I have a question not really related to the hardware side, but I was just wondering, are you using some kind of, from the software side of, do you use some kind of probabilistic kind of algorithms to take advantage of the fact that you have this kind of a device?
No, we have not. Hideo Ono's group with Kerem Chamsari and Supriya Datta actually use a very different electronic circuit. They took their sample off and ran it through a microcontroller and then sent it back as the feedback to the next MTJ. We think that it could be a lot faster using this kind of a circuit in terms of the coupling, because you don't have to go and do it all hardware.
Right. All right. Thank you.
Shakti, you can ask the question.
Hi, Prof. Sir. Very nice talk. I have a question about the material. So basically for MTJ, what should be the optimum thickness of the insulating layer?
Of the tunnel barrier.
Yeah, tunnel barrier, yeah. We're typically, overall getting, like 1.5 kiloohms overall. And that's with a tunnel barrier, more than a nanometer thick, but less than 2. If you get above 2, then, for the kind of sizes that we're interested in, diameters that we're interested in, the resistance starts, shooting up. But I think, what's really more important is getting those good interfaces with the COFIB. Okay.
When you anneal it so that you get the spin filtering effect and reasonable TMR.
I see.
Okay, let's have a last question. Raghav, you can unmute and ask.
Thank you, sir. My question is regarding this probabilistic computing. Usually in quantum computing, we have this problem of decoherence,
Yes.
which is introduced when when you have a large number of particles, there is a chance that you may have decoherence. My question is, in this probabilistic computing, we need a large number of particles, right? Because this is a statistical probability, so we may need
Right. It's not the large number of particles, it's the large number of events. So you need the time average. So we don't have coherence, we have the stochastic process. But if the stochastic process is happening fast enough and you average over a time window so that you get a reliable average that's not changing as you increase your window, then you get the statistical average. So it's a different approach, but you don't have to deal with the coherence problem.
Thank you.
I have a quick question. So wondering whether you have studied the temperature effect of this, because the superparamagnetic tunnel junction.
This is another thing where it's like everybody knows what happens with the temperature. It would actually work better at high temperature because it would flip back and forth faster. Yeah, I mean, one of the things that we like about this is there's a lot, there's a lot of subtle stuff there, but there's a lot of things that people in magnetics who know what superparamagnets are can really think clearly about what's going to happen and how you control it. So it takes advantage of a lot of things that we know and love.
Okay, good, very nice. Thank you. So let's conclude the talk. Thank you very much, Sarah, for an interesting talk. And now we will be having 3-4 minute break, and then the next talk will be given by Professor Rajiv Ramanujan. Yeah, it's 10:30 now. So welcome back. So next keynote speaker is Professor Rajiv Ramanujan, who will talk about accelerated discovery of magnetic materials. He is a professor in material science and engineering at Nanyang Technological University. So let's welcome Professor Ramanujan. Yeah, please.
Thanks, Varun. Today I will be presenting some work, our recent work on accelerated discovery of magnetic materials. And let me get started right away with this topic. So just as an outline, I will introduce the topic and what are the key challenges we are facing broadly in magnetic materials and our approaches to discover new material compositions by the use of additive manufacturing, by the use of spark plasma sintering, and chemical flow synthesis to develop a variety of compositions to explore the composition space in an accelerated fashion. There are also aspects related to thermodynamic modeling discovery, which we have used for high entropy alloys, and some short results on using data mining, using machine learning to discover new compositions. Of course, when we have the experimental results, we can couple these experimental results with the data required for machine learning. So it's called data fusion. So I think in this audience, I don't need to stress this. Essentially, of course, magnetic materials are used in many different applications. The interesting point is that in some of these next generation applications, we not only need magnetic properties, but we also need better mechanical properties. For example, if they're subjected to extreme service environments, we need sometimes higher elevated temperature compared to what is available presently. And of course, resistivity, electrical resistivity has to be optimized for AC applications. So the next generation of, for example, motors or other devices requires a combination of properties. It requires, in addition to magnetic properties, mechanical properties, electrical properties, thermal properties, high Curie temperature, etc. So how do we look at this multi-property new kind of requirement? So in this case, for example, if you want to have motors, then you definitely need, if you want to have high frequency motors, you definitely need to worry about mechanical aspects. You definitely need to worry more about electrical resistivity issues. So in short, we need to introduce other factors, other properties in addition to magnetic properties. So how do we go about finding out new compositions that can satisfy this kind of combinatorial requirements? There is a challenges because, for example, if you increase the strength, the coercivity also increases. If you if you try to change the magnetization, typically the magnetization is inversely related to the resistivity. So it's difficult to optimize all the properties for a given composition, because in some compositions have good magnetic properties, but not good mechanical properties, etc. So what we want to do is to solve this problem using AI in addition to the experimental parts. So for example, in the case of a soft magnetic material, even the magnetic properties themselves vary with position. So you would actually ideally like a graded composition in order to optimize the property, the spatial properties. So there are many new challenges which are coming up for the next gen magnetic components. But the traditional approach to developing this has been very slow. And to solve this problem, we would like to take up an approach of rapid development. We would like to explore a large number of compositions and we would like to look at graded materials in order to spatially optimize the properties. So how do we go about this? We used 3 experimental techniques. One is lens, which is an additive manufacturing technique. The second is using spark plasma sintering of powders to produce a graded sample. And the third technique is chemical flow synthesis, which we use for preparing samples which are, let me see if I can find the pointer. Right. So we use 3 different techniques. One is the lens technique, the SPS, spark plasma sintering technique, and the chemical flow synthesis technique. We also use different characterization tools in order to accelerate this, these processes. Okay, so let's get started with the high throughput additive manufacturing approach. So what we do is we produce samples. For example, you can see here, which are basically pillars. And these pillars, using this additive manufacturing technique, we can change the composition from bottom to top. So as you can see, a single sample contains a sandwich, many different compositions. So in one sample, you can have a layered structure, which has various compositions. And what we do is once we produce this, we can use our accelerated methodologies to study the crystal structure, for example, because crystal structure is often related to the properties. So we've prepared this for the case of iron, cobalt, nickel, which, as you can all know, is a very attractive system for finding new materials because it combines all the 3 ferromagnetic elements. So we prepared graded compositions and used rapid X-ray technology to find out what is the crystal structure. We could also rapidly find out the grain size, which is related to both the magnetic properties and the electrical properties and the mechanical properties. Then we used we determined the magnetic properties and the electrical properties for this entire ternary space of iron, cobalt, nickel. So we could map the MS, saturation magnetization, the coercivity, and also the electrical resistivity. So by these methods, we could obtain the, we could identify new compositions which have good combinations of, for example, magnetic properties and electrical resistivity. So for example, cobalt 30, iron 60, nickel 10, or cobalt 10, iron 80, nickel 10 can give you high MS, low HC, and high resistivity. So we could find out these are the interesting compositions. We could also do mechanical properties using nano indentation, and again produce a map of the mechanical properties as a function of composition. So you can find out, for example, that this area in red has the highest hardness. So that's a promising from the strength perspective. We could also relate it to grain size so that we have some kind of rationalization of why this kind of behavior is observed. So from all this information, we can plot what are called radar plots or spiderweb plots, which can quickly identify which composition is has a good combination of properties. So if you want a single property, for example, MS, then you can also identify which compositions have the best single property. But if you want a combination of properties, also you can identify using this radar plot materials that have reasonable MS, reasonable HS. So you can play this combinatorial game using this type of methodology. So this is an example of how we have used accelerated methodology to satisfy certain property metrics using additive manufacturing as the technique for sample prep. Then we prepared samples using a different technique, which is making powders of different composition, stacking them up, and then using spark plasma sintering to produce a bulk compact. So in short, this is the schematic. So basically you take powders of different compositions and then use spark plasma sintering to produce bulk samples. But these bulk samples have, of course, graded composition. So in a way, you create a materials library. So this materials library can be rapidly characterized and evaluated because it's basically a single sample. So we have done this again for the case of iron, cobalt, nickel, and we could identify magnetic properties. We could identify the Curie temperature. For the Curie temperature, we've developed a home-built setup in which we use a thermogravimetric analysis system as a way of determining Curie temperature. So we have we've published that result as well. So we can rapidly evaluate Curie temperature as well. We don't have to go through the usual PPMS route. And we measured the mechanical properties as a function of composition and using nano indentation, which is very fast, and electrical resistivity. So you can see that we've created a materials library in which we have a bunch of different compositions in the ternary space, and we've measured the properties, various properties. So here's where our results. So you can see that we can plot the saturation magnetization, the coercivity, the Curie temperature, the hardness, the Vickers hardness, and the resistivity. So typically for AC magnetic applications, you will prefer, for example, high electrical resistivity. Typically you want high saturation magnetization, and you can see that there are certain compositions which we have circled here, which have promising combinations of these properties. For example, you look at this ellipse here, it has reasonably good MS, low HC, medium TC. So it all depends on which properties are more important. So you can actually quantitatively decide which composition has the property set that you would like to select. For example, in this case, Fe30, cobalt 35, nickel almost equiatomic would have a reasonable balance of properties. So using this, we can again have this radar plot and identify compositions which have single good properties, right? So you can identify from this method in this ternary space. And it's not only ternary, you can go to quaternary, you can add boron, you can do other stuff. So this methodology is quite general and not only applicable to iron, cobalt, nickel, we are also applying it to the iron, silicon, aluminum, which is our classic transformer steel, and trying to find out new compositions which can have excellent combinations for the iron, silicon, aluminum case as well. So this is a broad methodology which can be applied to other material systems. So this was using spark plasma sintering. We also use chemical synthesis. So I'll go through this. So we've developed multi-channel flow devices, which you can see here. So using these multi-channel flow devices, you can see that we can mix precursors. So we start with three, in this case, we start with 3 iron, cobalt, nickel precursors, and they get mixed in various ratios here. And you can get, in this case, 7 outputs with different colors. So you can see that by this method, we can actually create a whole range of compositions readily. So just by chemical methods, in this case, we're lucky because iron chloride, nickel chloride, and cobalt chloride are easily reducible. So you can perform a chemical reaction within this device and produce the requisite magnetic nanomaterial powder. So now we have the powder produced by this chemical method. And you can see here that it's pretty fast. We can produce different powders. And once we have this, these powders, this is the entire device. We can make enough sample for measuring mechanical properties. In the past, people had done this kind of work, but there was insufficient sample mass to measure mechanical properties. In our case, because this is a high flow rate, we can produce sufficient mass to also conduct mechanical property measurements. So then we produce these powders. You can see these powders which have been produced using this method, and we can examine their crystal structure. And you can see that we can see a variation in the crystal structure from one output channel to another output channel, from FCC, BCC, FCC plus BCC, and FCC plus HCP. So in a relatively short time, we can scan several compositions in this iron, cobalt, nickel ternary space. So this is just for the powders. But then we can also go further, and we want to quickly know whether something is magnetic or not, because we are now screening. So we have set up our own home-built quick magnetic force measurement system. So as these powders, as these materials come out in the powders are produced, we can use this magnetic force measurement, which is basically a permanent magnet connected to a force sensor, to find out which material is more likely to be magnetic. So this is a screening process in which we are able to sort of filter out which compositions are more likely to be attractive. So these are this is some technique which we have developed in our lab. And of course, if you look at it from a physics standpoint, the force that the permanent magnet exerts on this powders is related to the permeability and other properties of the powders. So once we have produced these powders using this chemical approach, we then subject this to spark plasma sintering. So now we have a graded sample produced by this chemical method, and we can make bulk samples. We can make 3-layer samples, 4-layer samples, or in principle, we can make any number of layers. And we sinter them so that we get a bulk material which is easy to characterize and evaluate the properties. So again, we've looked at, these are some of the compositions that we have looked at from this chemical perspective. And once we've done that, we measured the properties of these in this ternary space. So for example, we found out the crystal structure. We can find out the grain size as well. We found the saturation magnetization, coercivity, hardness values, elastic modulus. So we can identify these properties in the system, and we can identify certain promising compositions in this ternary space which have a good combination of properties. So in this case, for example, these elliptical regions have a good combination of properties. Now, the properties are not optimized, obviously, because this is a screening method. So some of the values will not be the same as if you did a detailed study and a careful study of any one composition. But what this enables you to do is to create, to quickly zoom in on regions which could be studied in detail for attractive properties. So the approach in this is to, you have a huge continent and you want to know where there is gold. So you can't dig everywhere for the gold. And so you use this kind of methodology to identify regions which could be having the gold. So after that, you have to dig further to validate this methodology and to get more precise values of the properties. Yeah, so this is the strategy or framework around which we look at this this method. So we don't focus so much on the on what should I say, optimizing a single property, but rather identifying promising regions which show attractive properties. So now we've looked at 3 different methods of preparing samples and screening or filtering for properties. The properties that we've looked at are crystal structure, grain size, hardness, elastic modulus, magnetization, coercivity, and electrical resistivity. And so once we build up this property map, we can feed this data into AI and machine learning tools that we have developed. So I will now talk about some of the AI and machine learning tools that we are using to analyze this data. So first of all, we collected a lot of data from the literature. It's a very painstaking work in which for the iron, cobalt, nickel system, the data is very scattered, except for a few binary alloys, which are very well known, like permalloy and so on. So mechanical property data is in some handbooks and some type of journals, and then magnetic in other types of journals. So collecting this heterogeneous information was performed. So what we produced is basically a lot of literature data plus our experimental data. And then we feed this into the machine learning program. And then we have an optimization algorithm. Why we need an optimization algorithm is because, as I said, we want to optimize the properties. So depending on the specific application, the weightage you give for different properties can be different. So for example, if it's an iron cobalt alloy for high temperature aerospace applications, right, which all electric aircraft, for example, a lot of people are interested in all electric aircraft, then you need, for example, high TC, because you want to operate it at those higher temperatures. But if it's a room temperature application, you would give it less weightage for the Curie temperature. So depending on your specific application, one needs to optimize use an optimization algorithm to produce the right composition, which will give you the properties of your interest. So basically, we are able to incorporate not only composition in our data collection, but we can also introduce processing conditions, which is of great practical interest, especially for the case of magnetic materials. The properties tend to be very sensitive to the heat treatment or the method by which they are made, whether it's casting or forging. So these look like engineering details, but in reality, to produce bulk materials, you do need to identify these processing conditions. So from the literature data, we have actually been able to add this information. And we then find out what are the phases that we expect, which will give us good properties. And hopefully we can get a new composition with an optimal combination of properties. So we've gone through this process, and we would like to basically zoom in on the promising space. So let's see. So I'm just going to go through one example. We've done a lot of different algorithms which we have used. This is just one of them, which is called the random forest model. And we've tried other models as well. And you can see here that we feed in all this information that we got from the literature and experiments, and we have a training set which gives you some idea of how well we are able to map our data. So there's a predicted value and a true value, and this higher the R squared, the better the fit. And you can see our R squared values are pretty good. So for example, it's 0.94 for MS, 0.92 for HC, etc., etc. So we can actually use this random forest model and to create a model for our multi-property structure. Now, after we have created this model, we need to do an optimization. There are different optimization techniques. There's neural network and other techniques. So we've used Bayesian optimization to predict interesting compositions. So here's our Bayesian composition optimization for the same iron, cobalt, nickel ternary space. And the interesting thing about this is that you can specify what is your target based on your specific application. So for example, you may say, I want a 1.8 Tesla. I want coercivity of 1 Oersted. I want Curie temperature of 950 degrees C. I want this electrical resistivity. I want this tensile strength. And then you run it through this AI and machine learning algorithm. And more interestingly, you can also change the weightage. So for you, TC is very important. You can increase the weightage for TC, for example. Or if you think the tensile strength is most important, you can increase the weightage for tensile strength. So, and depending on the weightage, which, as I said, is the importance in the specific application, you will get different compositions. So it's a very nice tool for designers, because the same composition may not be useful for, typically not useful for different applications. In some applications, maybe permeability is the key. So then you would give it a higher weightage. So using these kind of Bayesian optimization tools, we can predict different compositions. So for example, one of the compositions, depending on a specific application, could be Fe64, cobalt 14, and nickel 21s. But it all depends on what's your target. So using this AI and machine learning, we can reach these targets. Okay, so sorry. So finally, I will summarize what we are working on. Basically, we are looking at accelerated methodology for materials discovery. It so happens we are focusing on magnetic, but this idea can be used for other properties, thermoelectric properties, dielectric properties. So it's basically a way in which we produce a variety of compositions. So in this case, we make compositions by lens, additive manufacturing, spark plasma sintering, and chemical flow synthesis. Then we use automated XRD, which can scan several samples at compositions at a given time. We use XRF and EBSD. Of course, there's always room for improvement in these things as tools come online. And then we use nano hardness, which is automated. And our Curie temperature, as I said, we've developed our own system using TGA for rapid analysis of the Curie temperature and get the resistivity values. And then we use AI and machine learning tools in conjunction with these experimental tools to build models. And we can also add thermodynamics to this to further enhance the accuracy of our models. So I thank you very much for your interest. Thank you.
Thank you, Prof. Ramanujan. Thank you very much. So now we have time for some questions. Audience, please raise your hand and I'll ask you to unmute and ask the question. Yes, Professor.
Very nice talk, very interesting talk. I'm curious about the generality of this approach. It seems that looking with iron, nickel, cobalt systems that you're looking at cases where the elements are highly miscible with each other. But you also mentioned, I think, aluminum, iron, cobalt, nickel. And I just think of, like alnico magnets, of having really beautiful, complicated microstructure where they get phase separation of different elements. Is your technique going to be applicable in those kinds of cases?
Yes, the answer is yes. You have exactly said the right thing. But even within the iron, cobalt, nickel space, we do have a variety of the crystal structures, because iron is BCC at room temperature, nickel is FCC, and cobalt is HCP. So even in this space, we are able to identify, for example, in this graph, you can see that we can identify some regions which are just FCC, other regions which are FCC plus BCC. So when you have a two-phase structure, the mechanical properties are obviously different. The resistivity is also different compared to a single phase structure.
Right.
Trying to model this would be a nightmare, but it's easy to, relatively easy to do by this technique. Now, extending this to quaternary or extending this to other ternary systems, for example, going beyond classic transformer steels, which are Fe 3.5 silicon typically, but people want to go to higher silicon, obviously, to increase the resistivity. So you have 6, 8, 10, but then what happens to the other properties? You cannot just focus on resistivity. And you can add other elements. Aluminum is just one example. This is one thing. The other thing is related to your Alnico question. There's another section of the talk, which for reason of time, I did not present, in which we have done the same methodology for high entropy alloys. And high entropy alloys have 5 elements. So actually we have, these are in the, let me see if, give me very quickly, let me see if I can show, these are in hidden slides here. Let me see if I can just go through this. So this is based on thermodynamics. So, we use thermodynamics as a way of screening which compositions could be interesting. And you can see exactly the system that you referred to. We have produced iron, aluminum, cobalt, nickel, iron. Yeah. So we've looked at this system, and we have we've done magnetic properties, we've done mechanical properties, and compared this to the literature. We can, in this case, we did it in more detail. We did actual stress strain curves. So you can see some of the results that we obtained. Exactly what you said is correct, that the microstructure is very fascinating and is very much related to the classic Alnico, but it goes beyond Alnico as well, because we are using this large composition space as exploration.
Okay, thank you.
Okay. Sabrit?
Okay, hi. Prof. Ramanujan, it's a very interesting talk, and I find it very tempting, like where you can change the, the gradient and then get the required property. Since I'm actually new to this one, I have a very naive question. So in the beginning, where you were changing the gradient of these magnetic materials, I'm assuming that first of all, that the whole pillar is going to be used for the application, the bulk material. Okay, and the question is, how much is there a limitation of that? The difference between the gradient between the stoichiometry of the material can be changed. Is there any limitation, or you can do whatever is required for it?
Yeah, so that's good. So in this lens technique, right? The thickness, each layer thickness is really quite small, because you actually the powders impinging on a substrate, and then the laser hits it. So you can get a very fine gradation in the properties using the lens technique. In the other two techniques, the composition gradient that you can produce depends, first of all, on the powder size, but one issue is that there could be interdiffusion between different layers, right? So if you are really want to be discrete layers, you need to put some kind of an inert foil, like tantalum foil or so on, to prevent this interdiffusion. In some other cases, it may not matter. A continuous distribution may be what you really want. So, it depends on your application. But I personally don't think it's a serious limitation from an engineering perspective. What I think you can get out of it on the positive side is that you can get a very beautiful, spatially optimized property set, which everybody wants. There's a field called permeability engineering, in which people want different properties. But even if you just think from a very simple point of view of a rotating electrical machine, which has magnetic components, the centrifugal stresses are obviously going to vary with position. So you want a stronger material on the outside compared to the core.
Okay. Yeah, okay. That helps. Okay, thank you.
Yonggi-san? San? Yeah.
Yeah, thank you so much, Prof, for the very nice talk. I found it very interesting. So my question would be, in terms of all these three different production techniques, I will assume all of them have distinct microstructures as well as the properties. Then if I understood your machine learning model correctly, you are trying to say that you imported all the obtained experimental results and put them inside the machine learning model for prediction. I'm just curious, how do you take into account of the microstructural differences and in order for them to work together for the machine learning model?
This is an excellent question. Actually, there are two parts to this question. One is, even within the literature, the results vary. And the reason they vary is because of processing. So for example, if you have a sheet of iron nickel, you can have different values of permeability, same composition, depending on how you process it. Just how much, whether cold work is 20% or 40%, will make a difference to all the properties. So the actual data is not as clean as you would like it to be, because we are doing the realistic part of adding in the processing. So the same, even if I ignore all my experimental data, when I look at the literature values, you will see a large variation in the structure sensitive properties like coercivity and strength. Okay, that's just the literature. And if you add in these kind of techniques, there's a variation within from technique to technique, because as you said, powder grain size is different, the processing parameters are different. So this makes, that's why I sort of add this caveat that what you're going to get are the trends, right? It's not, this number is like the, like a very physics based, like 25.375, it's going to be 25.375. But what you can do is to say it's hot, it's cold, it's medium, these kind of things which are valuable, because otherwise you would find it difficult to come up with good combinations of properties. So this is definitely a limitation of such accelerated methodologies, not only for my work, but in general, we sacrifice accuracy, or you can even say reliability, for the sake of being able to explore a big space.
Yeah, thank you so much for the nice explanation. If I may ask a second question, I'm curious about this third manufacturing technique in terms of this chemical flow. So if I understood this technique correctly, what is happening is that you dissolve all these different elements within fluids. Then after that, you turn these final fluids into powders before compressing them. Is that correct?
That's correct. So for example, you could take iron chloride, add in hydrazine or some reducing agent. And so by the time it comes out of the channel device, it is already iron. Then all we do is we just evaporate off the rest of the stuff. So if you have a ternary space, you will get a powder, as I can show you here. You'll get powders of the relevant alloys. So that's what we get.
Yeah.
So okay. Yeah, I think, thank you. We can have, because we are running late. So thank you, Prof. Raju. Yes, our next speaker is Prof. Wang Sheng Rancio from SPMS NTU Singapore. So he will be talking on tailoring low dimension magnetic ordering via atomic engineering. Yes.
Right.
Prof. Rancio, yes.
Yeah.
Can
you see my screen?
Yes, yes.
Okay, great. Yeah, I assume my voice is also clear. Okay. Good morning, everyone. Thank you very much for the kind invitation. So I'm going to discuss about some of our work on low-dimensional magnets. It's a Cvd grown 2D materials. My name is Wang Xiang from SPMS.
So Rancio, you can take, means we are running late. So your time start at 11:10. So up to 40 or 35 you can speak. Yeah,
okay,
25 minutes you can speak.
Okay, let's see how it works. So this is a relatively simple work. It's to be honest, quite straightforward. It's based on the Nature Communication paper we published last year together with Professor Liu Zheng. This is the outline of my today's talk. First, I give just 1 or 2 slides about the 2D materials. Then we discuss the fabrication, which is mainly done by Prof. Liu Zheng. And then we talk about structural characterizations, magnetization, and transport properties. Yes. For 2D materials, I think from material perspective is quite interesting. For the recent few years, there are a lot of research focused on this. I just list a few of them, but actually there are quite a lot of them. Especially the recent years, people try to explore using try to fabricate using different ways to get like low dimensional 1 or 2 mono layers of 2D materials. It's quite interesting because by the classical model, it's not stable, right? So that's why people would like to push across the boundary and see from physics point of view to see what kind of property, what kind of possible applications we can get. I just list a few of them. But also, if you look at the structures, most of these 2D materials or 2D magnetic materials, they are hexagonal. They have hexagonal structure, so there's kind of a clear indication there's a structural property. Very interesting correlation, not really correlation, relationship, because it looks like most of the 2D materials, if they are hexagonal, then they can be possibly magnetic. Okay, so for today, my talk, I'm going to discuss the iron-based 2D materials. It's iron cogugenized. Within the small family, there are a few possible, let's say, stoichiometry or compositions. Let's see, for example, iron selenide, but today's many of us iron telluride, FeTe. FeTe, or basically this whole family, is in recent years is quite interesting to explore new phenomena. So if you talk about broader perspective of the properties, it's actually a compound that hosts iron-based superconductivities, right? Iron-based, so there's iron, and especially with dope, with properly we can get bulk superconductivities. That's also a very at least in recent years is very hot topic. But if you talk about the magnetic properties, the whole family can give us also a wide range of the magnetic properties. Can be, for example, ferromagnetism, ferrimagnetism, antiferromagnetism. Right? Now, from structure point of view, there are typically 2 phases. One phase is a tetragonal phase, and the other phase is a hexagonal phase. Right? We want to see how we can play with the structure and let's say control the structures during the growth, and then see what kind of magnetic property we will be able to get. Now, talking about the structures or these 2 phases or 2 structural phases, the tetragonal phase, at least here, the top view you can see is tetragonal lattice, and hexagonal is obviously just a hexagonal lattice. I listed the top view and also the side view for you to have a better understanding. And for both phases, they are thermodynamically stable, meaning that we are able to fabricate them and they won't collapse, the structure won't collapse. So, okay, so then talk about the growth or trying to fabricate different phases, structural phases of the materials. So CVD is typically a very ideal, affordable, and a very quick technique that can use to check what we can do. And the structure, so the schematics of the CVD is already shown here. Its principle is actually quite simple. You have 2 glasses, you flow with these gases, you have these precursors. Eventually, on top of your substrates, you put it into the glass tube or quartz tube, you will be able to get. Although it's a structure, the schematics of the CVD looks very simple. However, if you really have some hands-on experience with the CVD, you will realize it's sometimes very nasty, right? Because there are different temperature ranges at different position or different location of the tube, the flow rate, the small contamination, and temperature gradients, and the temperature ramping up, ramping down rates, all can have a dramatic impact onto the CVD. Now, for this growth or FETE, we try to keep everything else as stable as possible, and then we monitor the growth temperature to see what different temperatures we can get. For giving different temperature, what kind of phases we can get. Now, what we in general, to summarize, on the low temperature side, we are able to get the tetragonal phase. On the high temperature side, we are going to get a hexagonal phase. But although it's a hexagonal, when we have a structure or have a flake that's grown at a certain size, it's got a triangular shape. But it's a hexagonal phase, not a triangle. It's a hexagonal lattice, not a triangle lattice. So this is the CVD growth. This we played with the temperature. As you can see, this is the optical images of the product. So if we have a low temperature growth, for example, 550 degrees C, you can see those are square crystals or square, either small flakes can get on top of the substrate. And if we go to the higher temperature side, you get the triangle or triangle shaped hexagonal face. Well, in between, of course, we will get some mixed phases. So we have a small phase diagram that if we change the temperature, we can get different phases. So to summarize, basically using CVD by playing with the temperature, we can not switch, we can determine different growth phases, meaning we can control the phases. Now, if we know the phases, then the next step is naturally we want to investigate the properties. Well, for the first step, we naturally need to see whether they are stable. So basically, we need to find out what is the window we can operate to study the whatever structural property, magnetic property, or transport properties. Because if we, for example, if the material just degraded or oxidized within a few seconds, then basically we're studying, for example, iron oxide, right? So and also if it's quite sensitive, we need to figure out a proper technique to protect the devices. So this is the result to test kind of the stability of the material. We put the samples in air. We just leave it there. We just take optical images of the devices. You can see as time evolves, especially for example, after 1 day, you can clearly see the sample oxidized. Right? Well, why is oxidized? Well, either because of water or moisture or the oxygen. But nevertheless, we know that within the first few minutes, we should have a small window to operate the sample to do a quick measurement or characterizations. So what we generally do, of course, first is to do the structural characterizations to see whether they are really tetragonal phase or hexagonal phase. To be specific, we need to know whether they are uniform, right? We get a flake. Well, then we need to know whether they are really everywhere tetragonal phase or everywhere hexagonal phase. So we did, of course, the AFM to measure the thicknesses, also the Raman to see whether they are structurally uniform. Especially for the Raman measurement, if you look at the right top images, this is the Raman scanning, so you can see that it's over the wide range of the whole flake. It's uniform. The phase is uniform. Right? So that means we are successfully getting a high quality FETE. And then we also measure the microscopic, the atomic structures. We use the TEM. So we captured the structure of the tetragonal phase and the hexagonal phase. As you can see from the high resolution TEM, you can see we literally get the atomic scale high quality can see the hexagonal phase and the tetrahedral phases are clearly visible under TEM. Of course, we can also do the lenimetry mapping. You can see the Fe and Te mapping. The Fe, the iron is uniformly across the whole substrate. I'm talking about the elements mapping on in the middle. Also, the Te element is also uniform, and the stoichiometry is also close to 1-to-1. This is another way to confirm that we are getting a correct stoichiometry. So now the property, the structural property is confirmed. So we get a high quality FET, and then naturally we need to go to the property characterizations. For example, the magnetic properties. Now to measure the magnetic properties, we naturally just go directly for MPMS or the magnetization measurement, or you can call it a magnetic moment measurements. We did a ZFC and FC, which is a field cooling and zero field cooling, to see the magnetic behaviors as a function of the temperature. This is a 32 nanometer thick tetrahedral FET, which is relatively thick. Of course, the flakes are all around the substrate. Initially we thought we could capture the magnetic property easily. Now it turned out that the result is not very clear. If you look at the data, right, clearly, especially the DMDT, we can maybe see a little bit of a neo temperature, which is consistent with the reported literature in bulk cubic, where the cubic orbital, so where the tetrahedral FET is supposed to be antiferromagnetic. Of course, we did some preliminary analysis. We see, okay, it's a antiferromagnetic phase. But what I want to see is this is one of the major issues when we study the 2D materials within the community by a lot of material scientists. So I personally see some literature in, for example, either in advanced materials or some even Nature Communication, for examples, when they try to study or pinpoint what is the magnetic phase of the 2D materials, they measure this and they make claims it's magnetic. But what I want to see is this also could be possible due to contamination, because you can see that substrate is typically 5x5 or something, or 5x1. Then whatever a small amount of contamination would introduce a large magnetic signal in MPMS measurement or magnetization measurements, and especially the 2D materials, the volume is super small. So this is, in my opinion, this is an issue, and a lot of, or some material scientists are making mistakes. So that's why what I want to claim is it is actually way more reliable to do the transport property. So, or do the transport measurement to characterize the magnetic properties. It's kind of the indirect way to measure the magnetic properties. For example, measuring the anomalous Hall effect. Because for using the transport properties, for example, here we fabricate a series of the 2D devices. We have the flake, we put the electrolyte on top of the devices, and we just measure the magnetic properties by passing the current or detecting the voltages. The thing is, when we measure the magnetization, we are measuring the whole sample, which is the sample, which is the flakes, including a big substrate. While here, if you measure the transport or the electrical properties, current only passing through the sample. So whatever we can pick up is only from the device. So or maybe speak from my own experience, sometimes when I do magnetic measurements, I see the result, I generally just throw away, although it looks like a ferromagnetic, because I know they are possibly, or they're almost 199% from the contamination. Okay, but anyway, we have the devices. With these devices on both the tetrahedral phase and also hexagonal phase. Of course, we use a BN, which is another 2D material, to on top to protect the device, because as I said, the device or the sample is not super stable within the in the ambient condition. So we need we fabricate the device in the glow box. We put the BN on top, and then we do the measurement. This on top of the tetrahedral phase, below is a hexagonal phase. This is the transport property measurement. As you can see, this is y-axis is the you can consider it as a resistance, or this is a sheet resistance. Horizontally, it's a temperature. As you can see, for the black curve, this is a tetragonal phase. Resistance goes up, and then at around 70 something K, and it goes down. So by checking the turning point, actually that is the magnetic influence on the resistance. Okay, of course, from if you check the literature, you can clearly see it is a neo temperature, which is a neo temperature for the antiferromagnetic phase. And for the red curve is the resistance versus temperature for the hexagonal phase. And somehow, let's see, if you check carefully, there's maybe a turning point at around 220 K, which is the Curie temperature of the ferromagnetism in the hexagonal phase. Well, if you think this is not a very convincing, so now I'm going to present the resistance, the whole resistance as a function of the magnetic field to have a to tackle the to confirm the magnetic property of these materials from a different perspective. Here, this is a serial measurement where we did a thickness scaling, and also we measured the enormous Hall effect. Let's check the results one by one and check what's the time, how much time I have. Okay, still have quite a lot of time.
Yeah.
Okay. Seems like I'm a little bit fast. No problem. On the left upper left side, that is a thickness scaling for the tetragonal phase of the FETE. So we change the we vary the thickness from, for example, 30 something nanometer to 5 nanometer. And you can see that for 30 nanometer, we have a neo temperature around something like 70 K. So, and then if we lower the thicknesses, and the neo temperature is going lower and even lower, for 5 nanometers go down to 45. This is kind of expected because as the thickness goes lower and lower, this long range magnetic order is harder to survive. And this is also consistent with other material systems, for example, in oxide, which I worked a lot. If we talk about hexagonal phase, which is ferromagnetic, and the 30 nanometer thickness is TC around 200 something, 220 K to be specific. And if we lower the thickness down to, for example, 4 nanometer, its TC is 170 K. It's also a bit lower, but luckily it still survives. Because if the thickness goes lower and lower, generally it's very hard to maintain the ferromagnetic phase. Of course, we did try to reduce thickness even further, but so far we have a technical challenges that we cannot preserve the high quality of the materials below 4 nanometer, because as I said, it's not stable. Although we did all the measurement and fabrication in the glow box, but it's still not inert enough to preserve those materials. Because it's just very active to oxygen and moistures. And then we measure the Hall effect. Hall effect is basically just the transverse voltage and function of the current passed through the device. The y-axis is the Hall resistance, x-axis is the magnetic field. When we sweep the magnetic field, I see that the tetragonal, the black curve, the tetragonal antiferromagnetic phase give us a flat line, and the ferromagnetic hexagonal phase give us a very nice anomalous Hall effect or hysteresis loop, the loop. So from the loop, we can clearly identify that the hexagonal phase, or confirm the hexagonal phase is ferromagnetic. We can also very reliably characterize its cohesivity. and also the coercivity as a function of the temperature. For example, here on the bottom left side, the hexagonal phase, which is here, the hexagonal phase, we can vary the temperature. We can see how the enormous Hall effect evolved as we ramping up the temperatures. Of course, by measuring the enormous Hall effect as a function of the temperature, we can further confirm the TC. So that's why we are able to confirm that the TC is around the 200%. Then we also the thickness scaling, or whether we reduce the thickness of the hexagonal phase, which is ferromagnetic. Of course, we are a little bit more interested in ferromagnetic phase because this can be a little bit easier to be applied into spintronics phase, although antiferromagnetic phase is also interesting. As you can see from here, that we reduce the thickness of the FET, hexagonal phase SET, we can still maintain the enormous Hall effect. For example, the 4 nanometer. Here is interesting that its coercivity goes a little bit bigger, not a lot, but goes a little bit bigger. And then, of course, we can plot coercivity as a function of the temperature. We can get a very nice characterization. Yes, so this is the magnetic phase characterizations. Of course, we can do a little bit more, which is, although in my opinion, not very useful, but we can push a little bit more. Like say, we can analyze the whatever saturation and also Hall angle. Maybe as I quickly go through here, the Hall angle can help us to identify the efficiency of the transition from the normal current into a normal Hall current, which can potentially be interesting for future strong or high performance spintronic devices. The calculation is relatively simple. I just do the enormous Hall conductivity over the longitudinal conductivity. Then you can get a Hall angle, enormous Hall angle. So, well, unfortunately, the Hall angle is not super big, so it's just fall into the big trend of different other materials. Of course, knows maybe in future for another different 2D material, we can get some exception. Okay, and that's about enormous Hall effect. So now I'm going to give a conclusion. So first, we are using the CVD fabrication to get 2 tunable phases, which is one is tetragonal and the other is hexagonal. The tuning of the phase is done by changing the fabrication temperature. We did also careful investigation on the structure of those 2 phases. It's confirmed that the structural property or structural quality of those 2 phases are quite high. We also did magnetic measurement, but what I want to say is our transport measurement is more reliable and it can give us more confidence in the magnetic property. If you look at the magnetization measurements, honestly speaking, I don't really have much confidence. So that's why whenever I do this low-dimensional small sample measurement, I always turn to electrical measurements. Or of course, there are other techniques, but magnetization measurements, in my opinion, is not does not give us 100% confidence. And last, I want to say that the magnetic order of this, for example, simple FETE, which only has 2 elements with a rich stoichiometry of 1:1, can be easily tailored by atomically engineering the structure of the 2D. Changing it from 2 tetragonal to hexagonal, we modify the magnetic properties. Of course, I'd like to thank my funding agent, which is MOE and NRF. And I appreciate the strong support from my collaborators, especially Prof. Liu Zheng, which is the last author of the Nature Com paper. He mainly he did the fabrications. He did the CVD fabrications. We worked on the magnetic and electrical measurements. So we have a very nice bond, and we have some nice publications out of it. So we really appreciate, and also others the students, theoretical support, and a lot of team members. And also, I thank you for your attention.
Thank you very much, Prof. Rancho. Very interesting talk. So now floor is open for questions. Let's have some quick questions. Yes, Saprit.
Hello, Prof. Rancho.
Hi.
Prof, where you were showing in the last one of the last slides the enormous Hall effect as function of temperature.
Yes.
So I have this question on the measurement. So since you are measuring this AHE at low temperature, do you consider the Joule heating effect or what current density do you use to make sure that the temperature stays at the ambience which you have put here?
Okay. So the question is about the impact of the Joule heating, which is the thermal perturbation from the current. So maybe I can answer your question from different, let's say, from different perspective or different levels. So first of all, based on our results, the Joule heating is never an issue because you can see the TC survives or the AHE survives over 200 degrees C. So that means for pure the Joule heating, there's no way we can heat up to the sample. The system is at 1.5 K, or the substrate or the heater is, or sorry, not the heater, not the sample holder is at 1.5 K, and there's no way we can heat up our sample all the way up to 240 K. So that's number one. But to be honest, we have a much more systematic studies on the temperature impact. Generally, if we do the measurement properly, the variation of the sample temperature is around 0.1 degree or 0.1 K. It's very, very small. Because for the samples, right, is on the back side is attached by a coat finger, which is copper, gold coated copper, and on top we also have we sometimes put the helium as a protection gas, which also helps to transfer the heat or dissipate the heat extremely fast. So that's why the temperature variation is super small. For the Joule heating, you also asked a question, the technical question, how much current will pass through the sample. We generally use 1 microampere, generally. Of course, if the device resistance is super small, we can ramp up to, for example, 10 micron or maybe even 100 micron, but that's about the limit we always use. So maybe you are thinking that maybe raising up the temperature, so raising up the current could help the measurement, but naturally we never did it. We always use the lock-in or the triggering to use a high frequency measurement, for example, 20-something hertz or 77 hertz to reduce the noise instead of using higher current. So that's why, to summarize, there's no heating, actually. There's no heating from Joule's effect. There may be a small variation of the temperature due to the sweeping of the magnetic field, but that's typically around 0.something, 0.1. 0.2 Kelvin.
Okay, thank you.
Thank you. Yeah, maybe soon you can ask question later, and now we have time for another next talk. So
okay.
Yeah.
Okay, thank you very much. I'm going to stop my sharing.
Yeah. So our next keynote talk will be given by Prof. Huin Xuan from National University of Singapore, and he will be talking on topological spintonics for spin orbit torque switching applications. Let's welcome Prof. Huin Xuan.
Thank you, Dr. Chaudhary. Can you see my full screen or it's splitted?
It's in the presentation mode, so I am seeing, yeah. Okay, you need to change it in full screen.
Sure. How about now?
Yes, it's perfect now.
Right. Thank you very much. Okay, so Professor Piram and Dr. Chaudhary, thanks for organizing this annual symposium. So in Singapore, we can also, get together to discuss about, some interesting topics in magnetism. So today I'm going to talk about topological spintronics for spin orbit torque switching applications. So if you look at the success of the, our spin transfer torque based MRAM is already in the market. So after its debut, it has been applied to like some Airbus due to the radiation tolerance and also some remote and health applications. And many companies are working on. And recently, if you look at some of the cases in 2018, IBM shipped flash core module with the MRAM buffer to enhance the system performance. 2019, Everspin Global Foundry in Singapore, they show 1 gigabit, sampling chips and already shipped to the customers. And same year, 2019, Samsung also shipped this MRAM embedded chip to Sony, and that is applied to Huawei smartwatches. So once you buy some of the Huawei GT2 model, basically you are using MRAM inside. So as academia now, we need to think about what will be the next generation magnetic memory technology, and a lot of people are interested in this so-called spin orbit torque based magnetization switching, because we can separate writing and the reading path, so which will improve our stability. The basic mechanism is still under debate. Some people argue it's coming from the strong Rashba field coming from this heterogeneous, interface. Some people argue it's mainly due to so-called spin-orbit effect. So once you apply the current in a high spin-orbit coupling materials, you can basically generate spin textures. And if you look at this interface, the direction is along the in-plane direction. And this direction is basically same also for the Rashba effect. So that's why it's so difficult to distinguish. But nonetheless, the bottom line is we can accumulate enough spin current density at this interface, then we can switch this above magnetic layer into one or the other direction, depending on charge current direction underneath. So how do we understand this mechanism? Basically, it's very similar to there's a banana kick in a soccer game. Once you hit your ball, on one side, basically you can rotate this ball, and when it moves, forward, not only going to a straight path, but it will also deflect to one direction. So in a conventional mechanics, this is called the Magnus Force. But in a solid state with the spinning, basically this is spin deflection, and we call this is a spin orbitronics. So this is the basic foundation how we can convert charge to sort of net spin current along this perpendicular direction. So once we summarize this field as a spin orbit torque engineering, basically we need to first generate this spin current using large spin orbit coupling materials. Some candidates, traditionally we have utilized the heavy metals. Nowadays people pay attention to this more interfacial spin orbit coupling materials. And also some interesting topological materials could be another candidate, which I'm going to focus in my talk later on. Even two-dimensional electron gas can also generate large spin current density. Once we generate, then we should absorb those spin currents. And traditionally, we've been playing with ferromagnets because we know how to fabricate and measure those. But nowadays, probably you've heard about lots of interesting works on ferromagnet or anti-ferromagnet because of higher efficiency as well as perhaps the large the density we can eventually fabricate. And then we can also even think about multi-layer concept. Capping was largely ignored, but depending on choice of materials, basically you can modulate the whole electric field in the structure that will affect via Rashba coefficient or some other effects. So also capping is important ingredient that we have to think about. So the main goal is to achieve basically low switching current in the whole memory structure. So that is inversely proportional with the so-called spinor angle theta as h. So we want to maximize this effective spinor angle or effective spin orbital field. However, at the same time, we need to think about in the total power consumption of the this memory. So for this, we need to also look at the device resistivity. So eventually, the most important parameter is we need to look at spin conductivity, which is a combination of spinor angle and device resistivity. So right now, the race is basically to find the largest spin conductivity material or system. So for this, in this talk, I'm going to more focus on these topological materials to generate this spin current. So if you look at the history of this interesting, so-called topological materials, starting with the graphene, with the Dirac-like band structure, this is semi-metal, spins degenerated. So basically not very useful for spintronics. Then, people invented or discovered this topological insulators. This is a Dirac insulator. It has very interesting surface spin momentum locking, which I'm gonna revisit in the next slide. Then people moved on the semi-metal, like a Dirac semi-metal concept. This is like a three-dimensional kind of version of graphene. Then recently, people also found this semi-metal. This is wire semi-metal. So if you look at the band structure, the joint cone is now separated. So this material also has interesting spin momentum locking, so it would be useful also for spintronics. So I'm gonna mostly talk about this topological insulator and wire semi-metal because both have interesting spin momentum locking properties. So starting from this three-dimensional topological insulator, one of the typical material is the bismuth selenide. So if you look at the band structure, it looks like this crossing, Dirac materials. But more interestingly, if you look at the, the detailed spin configuration on the right branch, it supports, this blue spin. If you look at the left branch, it supports this red spin. So if you look at in the real diagram, in real dimension, so if you apply the current along x direction, the supported spin will be y. But once we apply current minus x direction, the supported spin should be minus y. So basically, you can imagine this is like a spin highway. So naively, experimentalists, consider this as maybe a new material, which may give us a giant spinor angle. So that's why several groups investigated this topological insulator as spin current generation layer and how strong could be the spinor angle. The race basically started in 2014. A few groups at the same time reported, Cornell reported effective spinor angle 2 to 3.5. At that time, my group reported 0.01, two orders smaller. Tohoku reported 0.0001, so another two orders smaller than our report. UCLA reported up to 425, so two orders larger than Cornell, basically. So you can see, lots of, basically variations. Even we used the same method as a Cornell STFMR, we found up to 0.42 only at room temperature and low temperature. Room temperature, the efficiency was much smaller. So how do we understand these very, scattered, values from kind of similar materials? But of course, it depending on the measurement and, detailed material properties and so on. So we try to understand, this behavior by fabricating, more systematic samples in one group. So first, we notice thickness, could be key. So then we made starting from 20 nanometer sample, 20 quintuple layer, then narrow down to a few nanometer, and you can see effective spinor angle increase from 0.25 to 1.6. So, then we got to know thickness is very important. Then later on, this is this can be understood by the involvement of various bands. For example, if the film is very thick, then we have in a complex band structure, we have a bulk band, and also we have a two-dimensional electron gas. At the same time, this Dirac-like topological surface state. But once we scale down the thickness, then we push away this bulk band, because the bulk is getting smaller and smaller, but we can keep the involvement of this two-dimensional electron gas as well as this surface state. Once we make it even thinner, then eventually we push away this bulk band, and then most of the transport will go through basically surface structure and this two-dimensional electron gas. And because the K vector is the largest for this surface band, basically the most of the transport will happen through this interesting topological surface state, which will basically maximize the effective spinor angle due to spin momentum locking properties. This is a big contrast if you look at the conventional platinum material as a function of thickness. Typically they increase and then saturate. So this can be understood by the conventional spin Hall physics, and then we typically attribute the bulk band dominates. But on the other hand, if you look at this bismuth-selenide, thickness trend is exactly opposite, which indicate it is a surface dominant transport. So we just choose a quintuple layer because we need to think about effective spinor angle, but at the same time, junction resistivity. If we use two thin films, basically the effective spinor angle is very large, but junction resistivity will be huge. So the power consumption will be also very high. So by choosing this 8 nanometer, we deposit nickel ion on top, then we can chop down this nickel ion into a few or several pieces. Then with the different anisotropy coercivity. So all the black colors indicate the nickel ions pointing in this direction, and we apply charge current from left electrode, and you can see white domain propagate. Eventually we can switch into opposite direction. Now we apply current from right electrode, then we can switch back to this black domain, indicating this initial configuration. If you look at the switching current density, it's about 6 times 10 to 5th ampere per square centimeter, about 1 to 2 orders smaller using heavy metal cases, and we can extract the effective spinor angle about 1.75, which matches with the previous spin torque ferromagnetic resonance measurement. So we can now see this exotic interesting materials can even switch 3D ferromagnet, nickel ion, even at room temperature without any magnetic field, in this case, because we are using in-plane magnets. So there must be something more about this, scattered spinor angle values. And the other aspect could be temperature, because different groups reported the data at different temperatures. So first we investigated the temperature dependence. Then we found it can also vary significantly. If you look at this open circle, this is in situ method. So we grow bismuth-selenide and the magnetic layer in the same chamber without breaking vacuum, and you can see below 100 Kelvin there is an abrupt increase of effective spinor angle. We also use ex situ method, indicating we grow bismuth-selenide in MBE chamber, take it out, and then put a next sputter chamber, so there is an exposure to the air. And you can see in that case, the increment is very moderate and kind of a similar value across all these temperatures. So basically, they indicate, depending on the fabrication method, it can have very different temperature dependence. So we look at those using the TEM and then also EDX scanning of this profile, and then we found that there is an intermixing layer and also diffusion layer at the interface, which is always the case in a heterogeneous growth. And we found this intermixing thickness is 0.96 in case of in situ method, but ex situ we found is about 1.68, about 2 times thicker. So we will have a more intermixing and diffusion in case of ex situ, then which is also supported by this EDX scanning. And you can see basically there is more diffusion of cellulium into these, into these interfaces. So basically, we identify 3 roles of these scattered spin or angle values from topological. Number 1 is the thicknesses. Okay, so if you now go back to here, we can see Cornell used 8 nanometer. Initially, we used 35 nanometer. Tohoku used 300 micrometer, and UCLA used 3 nanometer. So you can see if they use a thinner film, basically, in general, they can see a much larger effect. But if they use very thick films, they end up with very small values. The other one is temperature measurement. Some group reported extremely low temperature, UCLA, and also my group, but later we also see those effects at room temperature and so on. And also in a different group used a different chamber, so the interface quality could be quite different. Even though we can see room temperature switching and very large spin or angle, but still we have a serious current shunting issue because bismuth selenide is about 2 orders more resistive than the nickel ion. So when we inject current, lots of current will be shunted through nickel ion layer without going through bismuth selenide. So those will not be able to generate the spin current. So to mitigate this, we try to use another material, wire semi-metal. As I mentioned, this, the Dirac cone is now separated. Then the property is metallic, but at the same time, it has a strong bulk spin-orbit coupling. So even though there could be some current shunting through the bulk, we don't need to worry about. We can still utilize a strong spin-orbit coupling effect. So this could, probably improve this current shunting issue in our devices. So basically, we do a very similar approach, having this tungsten ditelluride, prototypical wire semi-metal, then we deposit permalloy on top, then we, make some square magnetic piece, then apply current from left electrode, then look at the switching, and we can also apply current from right electrode, and we can go back to the initial configuration with the current density a few times smaller than that of a topological insulator. And once we study as a function of this, the tungsten ditelluride thickness, the current density, scale down. Once we convert to effective spin or angle as a function of thickness, it initially increases and kind of saturate, but we couldn't really measure much thicker because it's too thick. So if you look at this, the thickness trend now, this increasing trend and sort of saturating mimics that of platinum. So that indicates that we have a significant bulk contribution in this case. And at the same time, as I mentioned, the resistivity is about 1 order smaller than that of topological insulator. So the total power consumption, we have about 20 times improvement compared to this topological insulator cases. We can combine this with the geometric domain-wall pinning scheme. Once we have this anti-Nazi shape and then nucleate domain wall here, and then we can move back and forth this domain wall without applying external magnetic field, even for the case of perpendicular magnetic anisotropy materials based MTJs. So in this case, we can save about 2 to 3 times reduction in terms of switching current at 0 magnetic field because there is no additional energy to nucleate the domain wall. And eventually, it will be much easier also to integrate with the MTJ on top. So we just show this capability by nucleating domain wall. We can just flow current from left, right, back and forth. And then by adjusting the amount of the current density, the domain will always stop at this neck point, because in this round area, your current density will be much smaller due to the large area. So by doing this, we found there is about 3 times further reduction of the switching current density. And then in terms of power, we have about 1 order smaller power, consumption compared to rectangular channel. So by using this wire semi-metal, this is another one, MOT2, we can have 20 times power reduction. But using this anti-notch concept, we can reduce another 10 times power reduction. This material is interesting not only for the in-plane but also for perpendicular magnet switching, because it can generate the outer plane spin. So if you look at the atomic arrangement of this tungsten ditelluride, you can see it's very anisotropic. For example, if you flow current along this b-axis, then you look at your atomic arrangement on your left side and on your right side from the perspective of electrons, you can see it's symmetric. That means the potential is kind of flat. Now, if you apply charge current along a direction, and then from perspective of electrons, you look at the potential on your left side and right side, you can see atomic arrangements are very different. That indicate the crystal potential is tilted. So that indicate basically you can also have a tilted, spin current generation that will give us basically out of plane component using the current induced spin texture. So to look at those, we use CVD graphene, it's a wafer scale. So now we can, make many devices. Also, we can look at much larger scale measurements such as terahertz, which, include beam size of sub-millimeter, for example. So we can excite this material with circular polarized light. Then circular polarized light will couple with either spin up or down, depending on the polarization direction. Then depending on the polarization direction, the spin current will move only one direction. For example, upspin will move minus a direction, but downspin will move along a direction. So once we measure the emitted terahertz, basically we can look at the charge current oscillation phase, and left case we see positive peak, but on the right circular polarized we see negative signal from the terahertz signal. So that indicates basically the initial oscillating phase is 180 degree shifted. That means basically the coupled spin, depending on the circular polarized light, is opposite. So basically, this measurement, suggests that there is out of plane spin texture at room temperature in this tungsten ditelluride materials. Then we can also evaluate the same feature using conventional spin torque ferromagnetic resonance measurement. And by look at the anisotropic asymmetric component of rectified voltage, you can see our control sample platinum has sort of mirror symmetry if you look at this purple color. But if you look at now this CVD tungsten ditelluride sample with nickel ion, this purple color, there is a symmetricity. So that indicates there is outer plane spin texture. Then we can also use this material, CVD material now, and then we can deposit nickel ion. Then we can show this current-induced magnetization switching, which has been done from other measurements similarly. The importance of this is now we can use only a few nanometer tungsten ditelluride, not like tens of or even up to 100 nanometer using the Scotch tape method. So this is more practical for application. Last topic I want to briefly touch is magnon torque. Even though we improve this current shunting issue by utilizing more semi-metallic wire semi-metal, still the resistivity is about 1 order higher than 3D ferromagnet. So substantial current shunting is happening. How can we eliminate this current shunting completely? One way is to insert an insulating material in between MTJ and our spin source. Then the problem is even we generate the spin current at this interface, this spin current will never diffuse into this ferromagnet because it's blocked by this insulator. But if this insulator is an anti-ferromagnet and support some kind of angular momentum exchange via spin wave, for example, or quantized version is magnon, then this spin current can penetrate in this anti-ferromagnetic material and eventually reach this ferromagnet and give rise to torque. So that's the concept of this magnon torque. And if we can realize this, I think this can be also useful to mitigate the loss of complex interconnect issue in modern CMOS and then any semiconductor chips. If you look at the cross section of this chip, we have a functional layer in the first layer, and then we have additional 20 to 30 layers for interconnects. So basically the role of this interconnect is connecting from one device to the other device. So we have local contacts, and then even we have a global contacts and so on. So we need to make holes and then fill with the copper. So these holes are called the vias, and is very, very complex and difficult issue in modern semiconductor and any memory chips. If we can realize this kind of sort of wireless, I wouldn't say wireless, but using insulator, you can send some kind of quasi particle, and then you can switch eventually these isolated elements. Basically, we do not need to make a holes and then vias and then filling with this copper material. So probably we can relax the requirement of this interconnect and via requirement. So we put nickel oxide because this is very well known insulating anti-ferromagnet. Is also very easy to deposit using conventional sputtering. We use bismuth selenide to generate strong spin current. Then we try to investigate whether those spin current can penetrate this nickel oxide as a function of nickel oxide thickness. So once you look at this data using STFMR, those the solid dots. So initially, as soon as we put a few nanometer nickel oxide, we see effective spin-on angle immediately quench to 0, which is reasonable because if this is an insulator, spin current cannot penetrate. But surprisingly, once we further increase the thickness of nickel oxide, you can see, the efficiency is recovered, and then it can reach about 50% of the initial value, which is very surprising. With the 25 nanometer nickel oxide is very, very thick, but somehow we can, send our angular momentum to this above nickel ion layer with, going through this 25 nanometer nickel oxide. Then further increasing nickel oxide, the signal basically tapered out. Initially, it's very difficult to believe. Also, Repri pointed out, is it really true? So we involved opposite process. What we can do is a spin pumping experiment. So initially, we can pump spin current from bismuth selenide, from nickel ion by exciting with a femtosecond laser. Then we immediately quench the magnetism. So this is a demagnetization process due to very high energy of femtosecond laser. While the electrons cooling down, spin up and down, diffuse with a different velocity, then you can get a net spin current at this interface, which can be converted to some kind of magnon, excitation, then eventually can be converted to charge current due to the inverse spin-orbit coupling effect in bismuth selenide. So once you have the charge current oscillation, we can get terahertz emission. So we can just measure the amplitude of terahertz emission and then evaluate the amount of the conversion in this inverse process. So that is shown in this open circle in the blue color. So you can see the output trend is very similar to that of the STFMR. So now we can confirm this trend is trustable. And the other way to confirm this is really Magnum phenomena is the temperature dependence. Depending on the nickel oxide thickness, blocking temperature changes. And for example, 20 nanometer nickel oxide blocking temperature is about 200 Kelvin. And blocking temperature indicate, the spin fluctuation should be maximized near blocking temperature. So if you look at that sample, 25 nanometer, for example, nickel oxide, you can see the spin efficiency is maximized around 200 Kelvin, and the maximum temperature scale with basically with the blocking temperature. So that indicate the phenomena is indeed is a Magnum excitation. So we can now go, forward, by having this 25 nanometer nickel oxide, and we can put nickel ion, then we can chop down this nickel ion as an isolated square in the middle of the channel. So bismuth selenide and this nickel ions are basically separated. We can flow current from left electrode into only bismuth selenide, but we can switch this middle isolated nickel ion from one to the other direction by changing the charge current direction from right electrode. We can switch from this empty to black color, indicating we can go back to the initial configuration. So we demonstrate even we can switch with the 25 nanometer nickel oxide in between. And then also we can evaluate, by fitting this trend, what is the Magnum decay length and diffusion length. And then we found is about 30 nanometer of Magnum diffusion length in this nickel oxide material. Recently, we now try to understand what is the propagation speed of Magnum inside this nickel oxide. And by simply look at the time delay of this terahertz emitted terahertz, then systematically change this nickel oxide thickness, then we can find out the delay time and simply divide this delay time with the thickness of nickel oxide, then we can evaluate the velocity inside nickel oxide. Then we found it initially increases and then it saturates about 600 kilometers per second, then it decays. And this value is about one order larger than the previous estimation of 40 kilometers per second using inelastic scattering. Then they try to extract using dispersion relation. So it's an indirect measurement, but our measurement is direct measurement in time domain. And surprisingly, in nanoscale, Magnum velocity can be much larger than that of bulk estimation. So as a quick summary, I show you this interesting spin orbit talk. Can be applied to magnetic memory switching applications using interesting these topological materials, starting from topological insulators. Even though we were able to find a very effective large spin or angle, but there is large resistivity involved. Eventually, which leading to large power consumption. So then we move to wire semi-metals. We can utilize even bulk spin orbit torque, and with less resistivity, but still we have current shunting issues. So to completely remove this current shunting issue, now we use this Magnum torque concept. But the price we have to pay is the conversion efficiency is not, the same as the zero nickel oxide case. So if you look at, zero nickel oxide and then look at our maximum data is only 50%. So by having this, converting from spin current to Magnum and Magnum to something, because of this multiple conversion, basically we lose our efficiency to 50%. So the next question is, how do we improve this penalty, in the future research? So for this, I want to thank many of my group member and the previous group members who contributed, this data, as well as many international collaborators. Thank you very much.
Thank you very much, Prof. Hunshu, for a very interesting talk. So floor is now open for questions. Please raise your hand. Okay, yeah, Sakti, you can ask.
Hi, Prof. Yeah, thank you very much for this interesting talk. So I remember you told that this can be used for information storage, right? So I have a question. So is this good for heat-assisted magnetic recording? Because there also will use the pulse, a laser pulse, and here also you're using laser pulse, and there on you're having terahertz emissions. So will this be, will this material be good for that application?
Actually, what we are trying to demonstrate is a pure current-driven phenomena. So if you look at this experiment, we just apply current and then we can switch this magnet from one to the other direction. So in this case, there is no laser involved and so on. The laser experiment we just use to show the inverse process and to confirm, our forward, efficiency. When I talk about the forward efficiency, basically we inject charge current and convert to spin current and switch. So to confirm whether this trend is correct, we just use opposite process. So this is an inverse process, meaning we generate spin current and then convert to charge current. So this is spin to charge conversion. Previous, the spin to ferromagnetic measurement or even switching measurements are all charge to spin conversion process. Our application wise, basically we need to work on this charge to spin conversion. So this is for application. Spin to charge conversion, this is, this one also can be utilized as a generation of terahertz. This is another research theme in my group to generate terahertz using these magnetic layers. But for memory application, we need to use this left concept.
Left concept, okay.
Yeah, charge to spin conversion.
Okay, yeah. Thank you.
Okay.
Yeah.
Mohan?
Hi. Thanks for the interesting sharing. So you have mentioned that temperature and thickness does play a role in the spin Hall angle. So does this factor affect the crystal structure such as the 001 or more 1? So if so, is there a specific peak you guys are looking for in the position of the topological insulator?
Yeah, do you mean in nickel oxide?
For the bismuth selenide.
Oh, in bismuth selenide.
Yeah.
Basically, the direction wise, there is no strong dependence in bismuth selenide because it's a C3V symmetry. That indicate, that means basically you have hexagonal lattice, and depending on the the electron injection direction, you can have basically your momentum locking is always right angle to the electron injection direction. So that's the spin texture. So depending on the injected electron direction, there is no change. Okay, even though people reported some interesting up and down spin texture. Probably I don't have that one. Yeah. So basically, it doesn't matter which direction you apply. No matter what, you will always have this right angle, spin momentum locking in this case. So basically, it doesn't matter which direction we inject the electrons in this particular example.
Okay, thank you.
Yeah.
Okay, any more question? Great, it looks like we have covered all the questions. So yeah, before ending this session, first we will have a group photo. Thank you. Yeah, like this.
So the participants who were to take part in the group photo, please switch on your camera and pose.
Yeah. Yeah.
12 participants so far. Maybe we wait for another 10 seconds. Okay, whoever is interested, please switch on your camera and be ready for the photo.